Let me say just a few words about signal-to-noise ratio in functional MRI. First, some definitions. The signal-to-noise ratio is the signal that we're interested in divided by the standard deviation. First, we can think of this in terms of the spatial signal-to-noise ratio, that is the signal intensity at every voxel divided by the standard deviation of these intensities across space. However, for fMRI, what's critically important is the temporal signal-to-noise ratio. That is, the signal that we're interested in this case, the contrast between the activated and inactivated areas, divided by the standard deviation of the signal over time, the noise of that signal over time. So what's shown here are two time courses with different temporal signal-to-noise ratios. For functional MRI, we're particularly interested in temporal signal-to-noise ratio because this is what determines our detectability of the bold signal. Now, in a typical image, let's say for imaging a phantom like a bottle of water, these two would be directly linearly related. That is, with increasing spatial signal-to-noise ratio, we have increasing temporal signal-to-noise ratio. However, if we're actually imaging a live person, we also have what we could call physiological noise. That is, these are true physiological changes like the heartbeat and respiration that are there in the signal, but they're not the signals that we're interested in. And so if the signal-to-noise ratio increases, that is, if we have a better coil, or we go to higher field strengths, or we go to larger voxels, the signal, of course, increases, but the physiological noise increases as well. And as a result, we have this flat line in the temporal signal-to-noise ratio. So the overall signal, what we see with fMRI follows a curve more like what's shown in red here, initially increasing and then plateauing. Now we can write this mathematically as shown in this slide. The temporal signal-to-noise ratio is written as the signal divided by the standard deviation over time. And this standard deviation is the square root of the sum of the variances for thermal and physiological noise. This physiological noise can be written as a sum of both a bold and a non-bold component. That is, one component that is related or proportional to the TE and one that is not. If you put all of this together, you can rewrite this, that the temporal signal-to-noise ratio is equal to the signal-to-noise ratio divided by this square root of 1 plus lambda squared signal-to-noise ratio squared. So if this factor here is much less than 1, then essentially we have that temporal SNR is directly proportional to SNR. This is that thermal noise regime. On the other hand, if the signal-to-noise ratio is very large, then this becomes much larger than 1, and what this reduces to is just that the TSNR is just equal to a constant. And here's an example of that. These curves fit to actual data. This is showing the signal in the different compartments in the cerebrospinal fluid, the blood vessels, gray matter, and white matter. And you can notice that the model actually does fit what was the actual data pretty closely. Note also that the signal-to-noise ratio is lower in CSF than in gray matter and lower in gray matter due to white matter. And that's just because there's more physiological noise in gray matter and in CSF in particular. The reason I bring this up is because for a lot of the common imaging parameters, we're sitting out here in this region of the plateau. And therefore, if we were to go to higher field strength or get a better RF coil, we're really not increasing our temporal SNR very much, even though we have an increase in the spatial SNR. However, what we could do is go to higher resolutions, for example, or enable parallel imaging with a relatively little loss of temporal signal-to-noise ratio, even though the spatial signal-to-noise ratio is decreasing. So these are just some important things to keep in mind about signal-to-noise ratio, in particular